I'm Caleb Riggins.
I'm Alexis Adams, and our topic is resistors.
Okay, so a resistor is a two-terminal electrical component that implements electrical resistance inside of a circuit. Resistors are used to reduce current flow or to ease the movement of electricity. And so I'm now going to draw a simple form of a circuit that has a resistor inside of it. So a circuit will always have an EMF, which is just the electric potential difference. And then there's a circuit like this, and this is the resistor right here. And the units are always in ohms, and for EMF is always in volts. And so as current moves through this circuit, the resistor will impede the movement of the electricity as it goes around the circuit. So a conductor has low resistance and an insulator has high resistance. And so now we will go over an example problem of how resistors work.
Alright, so how we're doing is the power supply to the circuit, shown in the figures 8.00 watts. As you can see here, these are the resistors right here, R1, R2, R3, 4, and 5. So part A, we're gonna find the equivalent resistance for the circuit. And part B, we're gonna also find the potential difference across the battery. So for the resistors in parallel equation, it would be, we're gonna find R1, 2, R3, R4, R5. So R1 is 2.0 ohm. R2 is 11.0 ohm. And then R3 is 8.0 ohm. And then 4 is 4.5. And then 5, the last 2.0 ohm. And then for the equation, it will be 1 over R cubed. So P parallel equals 1 over R A plus 1 over R B. And then for the series equation, it would be R cubed S for series equals RA plus RB and
So for problem A, we're going to find the equivalent resistance of this circuit. I went ahead and labeled all my resistors for you. So we have R1 is equal to 2 ohms, R2 is equal to 11, R3 is equal to 8 ohms, R4 is equal to 5, and R5 is equal to 2 ohms again. Okay, so we're actually going to start off just looking at our first two resistors here, which are R2 and R3, and they're actually in parallel. So we're going to use our parallel equation to solve for them. Our parallel equation is 1 over R23 is equal to 1 over R2 plus 1 over R3. So this can actually be converted, and we're going to get R23 by itself by finding the inverse of R2 plus 1 over R3. So we're just going to set that to the power of -1. So now we're going to go ahead and implement our values for our resistors here. So again, we have R23 is equal to 1 over R2, which is 11 ohms, plus R3, which is 8 ohms. And this is all to the power of -1 once more. So our R23 is actually going to come out to be 4.63158. And of course I did calculations before this. So now our circuit, I'm going to redraw our circuit for us. And draw it in pink so you see it's a different circuit. So it's going to now look like this. We have one resistor across the top. And this is actually going to represent our R2, 3. And then we're going to draw the rest of the circuit exactly how we've seen it. All we're going to do is combine those first two in the top corner over there. So now we're going to continue our R4. We're going to go all the way underneath here. Oh, excuse me, I'm a little too far. All the way over here, we're going to have our R5 still. We're going to keep it going. And then that actually ends that loop there. We're going to add our other loop starting here with our resistor here. And then, of course, our battery here that has our current on it. So this will be our new resistor here. It's the exact same equivalent to the last. Now we're actually going to combine our R4, which is here, R4 with our R3 and our R2. So these two right here. So these two are sitting across each other on the same path. So they're actually going to be in series. So I'm going to actually use a series equation now to solve for the R2 and R4. R2, 3, and 4. So please excuse me. So we are looking at, what is it? R2, 3, 4 is going to be equal to R2, 3 plus R4. So we know R2, 3 from our last equation, which is here. So we have R2, 3, 4. Yeah, R2, 3, 4 is equal to our value now, which is 4.63158 ohms plus our R2, our R4, please excuse me, R4, that was very ugly, which is 4.5 ohms. After solving for this, our R2, 3, 4 is now equal to 9.1358 ohms. Alright. Next, I'm going to continue to redraw our circuit. Now combining our last two currents that we collectively put together. So now we're looking at a resistor here, right at the top. And we're going to come around. We have our resistor here, which is our our R5 still. We're going to come back around, and then we're going to go back one more time. And then we'll go ahead and draw my battery. All right, so this one at the top is now our R2, 3, 4. R2, 3, 4. So our R2, 3, 4 is actually sitting in parallel with this circuit here, which is our R5, okay? And so since it's sitting in parallel with our R5, we're gonna go ahead and solve with the parallel equation. So we're gonna go ahead and go 1 over R2, 3, 4, 5 is equal to 1 over R2, 3, 4 plus 1 over R5, all right? And then we do the exact same thing we did here, which was the inverse of it. So R2, 3, 4, 5 is equal to the inverse of 1 over R2, 3, 4 plus 1 over R5. All right, we're going to add our values in. So R2, 3, 4 is equal to R2, 3, 4, which we got from our last equation. So it's 1 over 9.1358 ohms plus our 1 over our R5 value, which is 2 ohms. So I actually forgot something in our last equation. It's actually going to be R power to the -1 power, because we have to find the inverse in order to get rid of this -1 here, this 1 over here. All right. And our value for this, which is R2, 3, 4, 5, will now be equal to 1.64066. All right. So I have one more circuit to draw. I'm gonna actually come back over here. I'm gonna put a line just so you guys know where I kind of stopped and had a little trouble. So I'm gonna come back over here actually. And I'm going to redraw our circuit, combining our R2, 3, 4 with our R5 And now I'm gonna add in our last, the last combination, the last resistor we have. Please excuse me. The last resistor we have. So then it's gonna be, all right, so it's gonna look like this. It's gonna be our new circuit, which is here. Here's our battery. And then here is the last two that we have. So up here, we're looking at R2, 3, 4, and 5, and R1. So last we're gonna combine these. They're on the same exact loop, so they're actually in series. So it's gonna be very simple. We do the R. We're gonna go ahead and do R, 2, 3, 4. I'm sorry. Ooh. It's gonna be our R equivalent because it's our R, all of our values equivalent to each other. All of our resistors, please. And then now it's gonna be 1 R, 2, 3, 4, 5 plus R1. All right, and then we're gonna implement our values. So it's R EQ is equal to 1.64066 plus R1, which was 2 ohms again. And then lastly, our REQ is going to equal to 3.64066 ohms. All right. And that will be our final value here. This is our R equivalent for this circuit here.
In problem B, find the potential difference across the battery when we're given power, which is P equals 8 watts. And with the formula for potential difference, to find the potential difference is power equals delta V squared over R. And with this equation, we have to manipulate it so we can get the delta V by itself. Delta V equals the square root, cancel the squared, P times R equivalent. And with our answer that was given in A, we'll use that to plug into right here to get our potential difference. So it's square root of our power times our answer we got right here, which is 8 watts times 3.64066 volts. And once we multiply that, we'll get
5.37 milligrams.
5.9679 volts as the potential difference across the battery.
I'm Alexis Adams.
I'm Daniel Grant.
I'm Caleb Riggins.
I'm Kayvana Davis.
Hope you guys learned a little bit about resistors.